We have two more speakers today before we have the rest afternoon. Very pleased to introduce to give the first of these Stein-Erik Fleten from NTNU.
Thank you, Chris.
I'm not just walking straight out. I left my cup of tea outside.
Thanks, Chris, and thanks for the invitation to come. So this is joint work with Ledsaak, Mehl, Røssum, Fram, and Ullrich. So it's an empirical paper on looking at the effects of capacity payments. So we've had a lot of talks on capacity markets and design and case studies and proposals for market design. So happy to give a different perspective here. The role of various people here. So Magne and Sigurd and Ola are the executors doing the work. Ben is consulted on expertise from the PJM system. He used to work for the market monitor for PJM, and also Ullrich used to work for the electricity industry in the US. So motivation is, as usual, these capacity markets are kind of interesting because we need these peakers to be there to follow the load, and we need these controllable units, these flexible units, both with low and high renewable share in the system. So for whatever reason, there are a lot of capacity markets out there, and one reason is the missing money problem, which in itself has various causes, right? So there's some kind of cap on prices coming from either policy or market technicalities or something, but it means that these peakers who are on a few hours a year have very little chance of recovering their costs. So some kind of remuneration for this capacity is said to be necessary. Not everybody agrees, but for this talk we take it as given. So the question is how much to pay for this capacity, and if you pay more, how much more capacity will you get? Take as a starting point that we observe on an annual basis the status of peaking plants here in the PJM case, and so the status could be that the plant is ready to operate, that it's in a mothball state, or that it's retired. So you can also switch between these states. So you can mothball a plant that's ready to operate, or you can start up a plant that's mothballed, or you can retire a plant. So these switches that happen on an annual basis in our data set is interesting because it tells us about the availability of these peakers. So we ask, how are these switches affected by changes in fuel costs, the intensity of competition, and varying environmental regulations? And how do the capacity payments affect these switches? So in summary, what we find is that there's less switching activity happening in total after 2007, and we have counterfactual analysis showing quantifying a connection between the capacity payments and the switchings. And we also find that the current levels of capacity payments in the PJM market gives quite strong incentives for the peakers to be ready to operate. So like I said, there's some controversy whether these capacity markets are really necessary. So there's one strand of authors who think that these are unnecessary because you could bid higher than the short-term marginal cost during the scarcity to get scarcity pricing, or you could get the demand side to participate and get scarcity pricing. So in principle, this should be possible. And others say that, well, you will always have these imperfections. You will never get full participation from the demand side, etc. So capacity payments are needed. So there are also speakers in this workshop that touch on these issues. Okay, so we observe these plants once per year, and we think of these decisions to switch between the states as a kind of real options model, where there's a profit indicator that is observed by the decision maker. It's going on over time, and if you start a plant that is ready to operate and you observe that the profit indicator is going down, well, you might reach a shutdown trigger level, in which case you shut down the trigger and you may pay a irreversible cost of doing that. And after that, then your plant is in mothball state, in standby state, and it's keeping in that state until you reach a startup trigger for the profit indicator, in which case you pay a startup cost or startup investment that you don't get back. It's irreversible. So it's on until you reach the shutdown trigger again, and if you go very low for the profit indicator, you may retire the plant permanently. So this is the kind of dynamics that we have in mind for managing these switches. It's a Brennan and Schwartz model. So there are three main operating modes. You could be operating ready and switch back to that mode every year, or you can switch to standby and stay in standby for a number of years, or switch back to operating mode or retire. So we have excluded from the data set any observations going directly from operating to retired, because we think that those decisions or those observations probably come from or driven by other things than changes in some profitability indicators. So just to flash the math here, this is because of the workshop. So what's happening when we solve the estimation problem is that we solve this nonlinear programming problem where the objective is to maximize the likelihood of observing the data that we have, subject to this relationship here, which is representing the real options model that we have for transitioning between the various operating modes. There's a choice probability involved here. That comes from introducing uncertainty in the payoff when making a transition decision. So there's uncertainty there that's observed by the decision maker, but not by us, the analyst. And this is quite standard within this structural estimation framework. Okay, so what's happening in words is that we maximize the log likelihood for observing given plant status for the given state variables that are listed here, subject to decisions being made according to our discrete time real option switching model. And then as part of this, we use k-means clustering to model the dynamics in the transition in the state variables. This represents how we think the decision makers believe future conditions regarding fuel costs, electricity prices, etc. will evolve. And what we get out of it is the switching and maintenance cost parameters that we're interested in. So in the core of this estimation is this cost to go function, this profit to go function here. So the profit to go is so the 1 year profit is the payoff, the profitability minus in the maintenance cost, and that's valid for the case when the plant was operating and you decide to stay in that operating ready mode for that year. If you decide to shut down and start up, there's irreversible shutdown and startup cost invoked. And if you go from standby to standby, then there's a maintenance cost in the standby mode that's being incurred. It's natural to assume that this maintenance cost for the standby mode is lower than the maintenance cost in the operating ready state. Also, if you do this switch either from operating to standby or vice versa, then you get only half of that year's profit and you pay the average of the high and the low maintenance cost. If you retire the plant, then you have half of that year's maintenance cost and you pay a retirement cost. Usually this is estimated to be negative, so there's a retirement value reflecting either the second-hand value of the thing or the value of replacing the unit. So in our estimations, we will keep these maintenance cost parameters fixed, but we'll have the irreversible shutdown and startup cost and retirement cost depend on other state variables. This is a picture of a peak plant in New York. It's 48 megawatts, I think. So it's typically a typical plant, gas-fired. They could also be fired by number 2 oil, which is diesel fuel oil, and jet fuel, kerosene. In our data, we have 859 different generators in 252 different power plants between 2001 and 2016, and our main data source is this Form 860, which requires annual filing for every plant owner over 1 megawatt in the United States. Yeah, so in this Form 860 we can infer once per year what the status of the plant is in for every plant, and we're looking only at peakers for this research. So what does it mean to be mothballed or standby? Well, the definition in the database is given here. So it says that you usually require some time and effort to reactivate the thing. So it's not ready for operation. Next up is a few graphs on the input data. So this is electricity prices from PJM, and we concentrate on the on-peak hours from 6 in the morning to 10 in the night, and we have data for PJM, and in PJM there's occasional marginal prices. We have collected prices per zone, and these are the codes for the zones in PJM. This is capacity payment data for PJM, and in PJM there's the name of the capacity market is Reliability Pricing Model, so RPM. This is prices that are valid for 1 year at a time, and the prices are set in auctions that happen 3 years in advance. So when you're cleared in this auction, you have to deliver. You have to have your capacity available for 1 year. And this market started up 2007, and prices are oh, it doesn't say here, but this is I think in dollars per I don't know per megawatt, yeah, per kilowatt. Yeah. Anyway, these are also per zone here. Yeah. So these are the prices that we see, and we don't have data on each individual plant here, but these are the prices that we observe in the market. And what we assume that these peakers do is that they make sure that they are knocked down in these auctions. So they need to clear, otherwise they would go bankrupt. So so we assume that these plants that are in our sample, they get these prices. All right, so these are the fuel prices, 3 kinds of fuel. The most important one is natural gas in blue, and then you have kerosene, jet fuel, and number 2, oil. And the most cheap one is natural gas. And what's been happening during this time period is, of course, the shale gas revolution. So, 2007 and 8, you'd seen a dramatic downturn in these prices because of shale oil and gas. Gas prices are from Henry Hub. The number 2 oil is from New York Harbor, and the jet fuel kerosene is data from the Energy Information Administration, U.S. Gulf Coast. And we use, as one of the state variables explaining the dynamics of the changes, the switches, is the annual change in the natural gas price. That's one of our state variables. Another of our state variables is the profit indicator. And the profit indicator is calculated from daily observations of spark spread. The spark spread is this contribution margin that comes from selling electricity, buying fuel, converting it into electricity using a heat rate, and then there's non-fuel variable cost, and then you have capacity payments. So you take the positive part of this spark spread and convert it into an annual number this way, using only on-peak, the 16 on-peak hours. So for this one, we get one observation of profit indicator for each plant on each year. We call it an indicator because it's a theoretical calculation. It's what the plant would have earned if it's operating, rationally. So it's not the actual revenues, but a calculated revenue. All right, so the exogenous state variables include this profit indicator, the change in the natural gas price, and we have 2 more, the intensity of competition, and a dummy for strict environmental regulation. And let's look at the intensity of competition, how we measure that. So that's related to the heat rate. So heat rate data is from the Energy Information Administration Form 923, which measures how much is being produced and how much fuel is being consumed. So this will give us about 1/3 of the heat rates, and then we use regression based on age and capacity to get an approximation for heat rates for the remaining 2/3 of the data of the plants. So we measure intensity of competition by looking at the heat rate that you have in your plant compared to the average heat rate in the relevant PJM zone. So if the C here is high, means that the intensity of competition is high. So the an important thing that's been happening over data analysis period 2001 to 2016 is changes in environmental regulation. So in 2003, you had the NOx budget trading program, which is a cap and trade program, and from circa 2011, you'd have the CAIR program, replaced later on by the CASPER program. These are programs initiated by the Environmental Protection Agency in the US. And it gives strong incentives to lower the NOx and SOx emissions, so it hits the coal producers in particular. And what's happening over time here is that gas-fired power plants, both peakers and combined cycle, also renewables, are displacing coal. So that's good. Anyway, we match the occurrence of these policies with a dummy variable. So it's 1 if we're in these years here where these new regulations are put in place. So that's a deterministic state variable. Okay, so here are all the exogenous state variables. You have the profitability indicator coming from the spark spread, and you have the intensity of the competition. You have the annual change in gas prices, and you have the environmental regulation. And these are some summary statistics for the state variables. The average intensity of competition is 1. The average payment from the spark spread, annual payment is $37 per kilowatt. Average change in the gas price is 0, and about 0.38 for the average environmental variable. Right, so here's an interesting table regarding switches and profitability. So we're looking at switches from the OP state in these 2 columns and switching from the standby state in these 3 columns. So here you switch from operating ready to operating ready next year. And we have a lot of observations for that, so that's the most common one. In fact, 98% of occurrences happen there. And the average profitability in the 2001 to 2007 range is $12 per kilowatt for staying in the operating ready state, and the $6 for switching to standby. So this makes sense. If it's less profitable, you switch to standby. And the same you can see here. If you're in standby state, then you move to the operating ready state if the profitability is high, and you move to retirement if the profitability is low. If you look at the latter part of the sample, 2008 to 2016, you find that there are much fewer observations. So there are only 4 observations here and 15 observations here. So this could explain the lack of sense that we can make out of these numbers, because here it goes the totally reverse of what we would expect, both in terms of energy-only profitability and profitability including the capacity payments, which we can see are substantial compared to the energy-only numbers. Okay, so this is a graph showing the switches that we observed. So the colored lines are the switches. So this is switching from operating to operating, and it's pretty stable in the latter part, and then it changes more in the first part of the sample. This is from operating to standby. Fewer and fewer over the years. The green and the blue would be interesting here. So the green is standby to operating, so startups, and this one is retirements. And the gray bars are probability distributions for the profitability indicator. So 2001 was a quite profitable year with high variance, and 2004 was a non-profitable year, with much of the probability mass in 0. And there's a big difference between the 2001 to 2007 switchings compared to the latter ones. And I've already indicated what's been happening. There's environmental regulations affecting this, but also the shale gas has changed the market a lot. So when we estimate the switching cost and maintenance cost, what we get for PJM is $9 per kilowatt for maintaining a plant in the operating ready state, and it's very low for the standby state. Also quite low cost for irreversible switches, and there's a negative cost for switching to retired state. So you get salvage value here. We can compare this to numbers that we get if we take all the New York ISO and New England ISO also, and we get almost the same numbers. So finally, getting to the end here, how is switching behavior affected by state variables? Well, so let's look at the barrier to start up a plant. How is the barrier to startup as perceived by the decision makers depending on the intensity of competition? So if the intensity of competition goes up, well, the barrier goes up for starting up, and it goes down for the exit barriers. So that's good. What about the change in the natural gas price? Well, if the change is positive, then the barrier to startup goes up, and the barrier to exit goes down. So that's also natural. If you look at the regulatory indicators, so if there's strict regulatory environment, then the barrier to startup goes down, and we believe that's because it hits the competition harder than these gas-fired power plants. And it goes up for the exit barriers, which is also natural. These are results that are consistent with a real options kind of thinking here. So let's look at some counterfactual analysis. This is the increase in the share of availability of plants as a percent. If you change the actual level from 100% up to or down to 0. So these are the changes that happen in plants being in standby and operational mode. This is changes from operating to operating or operating to standby, and here we also see that the higher the capacity payment, the more attractive it is to keep the generators available. For the standby state, it's not as interesting. So here are transitions from the standby state, and there are very few plants in the standby state. So one thing we can see when we increase the payments from the current level is that not much is happening. So the difference between the green and the red is very small. So here we increase the payments from 100% to 150%. So you can't get much higher. So this we conclude from this that the payments are generous. So natural gas price changes, competition intensity, and environmental regulation change the barriers to entry and exit in expected ways. And it's important that regulators understand the cost structure here. Peakers are dispatched more often, and a counterfactual analysis quantifies the effect of capacity payments on availability. And we find also that the incentives are quite strong. Maybe they are too strong currently. So that's what I had. Hope to have good comments from you guys and the Cornel in particular. Thanks.
stole my thunder. My question was going to be, are these payments too generous? And you answered that about 2 minutes ago.
Yeah.
But there were some data issues that gave me pause. On page 3 of your paper, you have demand response as the dominant entry into the market, but didn't pay any attention to it. I was wondering why you didn't, and what would you do if you wanted to pay attention to it?
Yeah, it turns out that demand response seemingly is quite, quite cost-efficient way to have capacity available, since most of the new capacity in PJM that came about after these changes after 2007 is in fact demand response. So, well, that's a good thing. Now the question is, what does it mean for me and our research questions here? Because we're interested in these peakers and how payments to these peakers affect their behavior, right? So how would it change if we try to include demand response there? Well, that would be challenging because we need a systems model to model the competition then between demand response on the one hand and peakers and other capacity sources on the other. So what we do is simply take the prices as given, assume price taking behavior, and hope we can get away with that.
And my last comment is that table you put up, which is table 2 in your paper, has an average profitability that seems to be unbelievably high from going from standby to retirement.
Yeah.
How do you get that?
Well,
I don't even know how you can make any profit going from standby to retirement.
I think it's this table here.
That's it.
Yeah.
Average profitability of $60 when you go from standby to retirement.
Yeah. So
60. I forget.
yeah. So these are quite few observations, and the retirements must have happened disregarding the profitability somehow. There must be other factors driving the retirements than the profitability. Must be it's just broken or something.
But I don't understand how you get. I mean, if you're in standby, you can't make any money in the energy market.
Yeah, but remember how we calculate these numbers. It's not real profitability. It's just what you would have gotten if you were available and if you were cleared in the capacity market. So if you're retired, of course you can't make any money. But these calculations are, if you were available, what would you have earned?
So you would have had to move from retirement to standby to operate.
Yeah.
Any questions from the floor?
Sorry, perhaps I didn't understand this correctly, but you used the actual realized prices to calculate profitability.
Yeah.
And that information was not available at the time when the shutdown decisions were taken. It was the best prediction. Is there a big difference between the best prediction that was available at the time and the actual realization?
Good question. So these numbers are our model for indicating how we think the decision makers in a broad view are making decisions on switching. What they do in reality is try to forecast things and use various types of models for that. Yeah, we are, like you say, we're just using the prices as they are, and using that as a model for how we think they form expectations regarding the broad profitability in making these switches. So the alternative for us would be to do as you recommend, to make a forecasting model. But any forecasting model needs to use the information that's available. And what kind of information is available? Well, you have price levels now in the gas market would be an important indicator. And somehow that's already reflected in what we do. And there are other indicators for the electricity market, such as projected reserve margin and things like that. So, yeah, some of our other papers try to incorporate these other variables as well, but we find that this is a rough, good approximation.
Just can you say something about renewables? Because PJM, renewables is basically round-off error as far as penetration levels go. Why you chose PJM and how you think it would shift if it went to CAISO or something?
Yeah, I'm selecting only peakers in the sample, looking only at their behavior. What's been happening in PJM has been expanding, also into areas there are some renewables. I don't know. The environmental regulations have implicitly, suppressed coal, which usually gas has taken its place, but to some extent we can expect that renewables has also done that. So, and your question is, okay, what about renewables? How does it affect the results here? Well, you could think that, well, there are, when you do these retirements for these peakers, maybe some of the alternatives in some cases would be upgrading a hydro or other renewables. And if you can do that, typically that could be quite cheap, and then it wouldn't matter that these numbers are high, right? So it could be those things like that. Yeah. Other people need to answer, okay, how much capacity payments do you get if you're renewable in this market? I don't know.
This seems often as the penetration levels get above 50%, peakers become even more important. So you might need even more capacity payments to keep them alive.
Yeah. So I'm hoping that these are interesting numbers.
Yeah, I just had a question about these unexplained retirements. Did you look at the residual values, how they change over time?
Residual values of what?
Well, of the whole. I mean, the plant, when you retire, you can sell the land, you can reuse it, and so on. This can change a lot, I guess.
Yeah, what we should do is look at these retirement and see what happens at the site, because I would expect in many cases that what's happening on the ground is that you replace it with some other unit that's much more modern and more efficient. And the reason you want to do that is the old machine is old and getting not so reliable anymore. So it has value to you to do these switches, and that's why we see these negative numbers. So I think we should look more closely into each retirement case and see what happened after at the relevant site. So that's a good observation there.
So, Stein-Erik, this is a thing which I'm probably just missing in the analysis here. But are we looking ahead for the capacity prices, which are the dominant? The capacity prices are enormous here.
Yeah.
And we know what they're going to be 3 years out as a decision maker. Is that part of your decision process, or does that kind of not matter in some sense?
It does. We do have dynamics for the capacity payments. So what we do, this space is multidimensional. So we use k-means clustering for modeling the transition from one possible state to another. And so these capacity payments, they're not shown here, but yeah, they are known 3 years ahead, but still they are unknown beyond that. So I think that's how we do it here. Based on the historical transitions, what are the possible distributions for how you can go from this level 3 years ahead now to the next level? So that's how we do it.
I think we've got one more quick one from David.
Oh, very quick question. Why didn't you put the age of the peaker in as one of the explanatory variables for exit?
Well, we hope that the age of the peaker is coming up in the heat rate. The older, which is time varying. So the older the plant is, the less efficient it is. The worse the heat rate is. So I hope, yeah, the age aspect is indirectly there.
Yeah, perhaps interesting little example that the difference between correlation and causation.
Mm-hmm.
With what the variable is versus breaking the control.
Yeah, we do not have a sophisticated model for that. So there could be a state variable for a given plant that tells us about the risk of breakdown, but that's a more advanced model than we would be able to do here.
Anyway, coming to the hour, so it's time to start here. Thanks, Stein-Erik again.